Good morning, students. Welcome back to another Waidsum Academy video. Today we're going to be doing chapter 13 of the IGCSE syllabus. In this chapter, we're going to learn about the periodic table. So let's get on to it. So there are many questions that have been asked based chemistry. And in this chapter, we are going to learn about the elements and how it's arranged in the periodic table. So, section 13.1 is how elements are arranged in the periodic table. The periodic table has two things, groups and periodic table. But what you should know is, what is a periodic table? The periodic table is a list of elements arranged in order of increasing proton number. The periodic table divides the elements into periods and groups. A period is a vertical column of elements, while a period is a horizontal row of elements, while a group is a vertical column of elements. And when they say that the elements are arranged in order of increasing proton, it means that as the periodic table, each element has different proton numbers. And the periodic table takes these elements and arranges them in an increasing order and places them in an organized tables, forming the periodic table. Now remember when I said that the periodic table is split into groups and periods. Now in the periodic table, here's an image showing, this is an image showing the periodic table. If you haven't noticed, there are arrows showing groups and periods. Well, I can explain to them what they mean. If the groups are a vertical column of elements, meaning that they are vertical and they are shown of the periodic table has split into the periodic table has split these groups into 8 parts. Now these 8 parts are written in Roman number, and each group has its elements organized from top to bottom, with the top having the lowest proton number and the bottom having the highest proton number. And for the period, it's the same thing, but instead of it being vertical, the periodic table is horizontal. It has a horizontal row of elements. Let me show you the horizontal row of elements, while the group is vertical. Now this horizontal row of elements are in periods, and they're represented with normal numbers, as you can see right here. And as they are arranged from left to right, with the left being with the lowest proton number and the right having the highest proton number. And with this, you have the periodic table arranged. So that means that each element has specific proton number. Let's take for this element, for example, this SR element. If you notice, it's in the middle of the group. It's in the middle in the group, but in the beginning in the period. Because in the group, the element with the lowest proton number in its group is beryllium with 4, with a proton number of 4. While, however, in its period, it is one of the lowest, the second lowest. As you can see, as it goes on, the highest is hexagon with a proton number of 54. While here it's only in the second lowest. So this is how the periodic table is organized, and here we're going to learn the periodic trends. So now we've done with section 13.1, we're going to learn about section 13.2, the periodic trends. And here we're going to describe the change between metallic to non-metallic. Now if you haven't noticed, in the periodic table is split into 3 colors: yellow, green, and blue, with the yellow being metals, blue being non-metals, and green being metalloids. So all the yellow part is metals. We'll pause. You're probably having a question right now. How come the groups have a stop in between this section and continues on from here? We have group 1, group 2, then the entire of this part is skipped, and it continues from here with group 3, group 4. What are these things? This part is called transition metals, and we will learn about them later in this chapter. Transition metals. We'll learn about them later on as we're studying this chapter. But for now, we are going talking about these parts. Now we have metals, nonmetals, and metalloids, and each of them it has a specific trend in the periodic table. Now, if you notice the properties of elements across period 3, period 3 means this period. As you can see, the period is 3. This is period 3. This entire part, starting from here, is period 3, and it has a bunch of elements, shown right now. It has sodium, magnesium, aluminium, silicon, phosphorus, sulfur, calcium, and argon. Now, in this period 3, you can see that sodium has the lowest proton number, while argon has the highest. And if you notice, this period consists of both metals and metalloids and non-metals. So one thing you should understand about this is actually has a specific trend, as the elements with a lower proton number tend to be metals, and they form basic oxides. If you want to learn about the nature of oxides with elements of metals and non-metals, I highly suggest you watch our chapter 12 video. There I talked over about the acids, base, and oxides, and how metals produce basic oxides and non-metals produce acidic oxide. Non-metals produce acidic oxide. Then we have amphoteric. Amphoteric means it's an oxide that can react both with base and acid. Now, anyways, the metals produce a basic oxide, and they have metallic properties. But as we go on in the period or the group, each metal has its own group, it slowly transforms from metallic properties to non-metallic properties, producing an acidic oxide. So all these are non-metals, while these are metals. So you're wondering, what is a metalloid? A metalloid is an element that has properties of both non-metallic and metallic properties. So now let's move on to how metallic properties change down the group. Going down a group, there is an increase in metallic properties and a decrease in non-metallic properties. A group. So remember, we're not talking about period anymore. This is a group. A group is a vertical, not horizontal. Now, as we go down the group, there is an increase in metallic properties and a decrease in non-metallic properties. This is because going down a group, the size of the atom increases. Hence, the outer shell electrons of an element will be further away from the attractive force of a nucleus. Remember how an atom is built? We have nucleus at the center and a bunch of outer shells. Now, in the lower side of the group, the lower group have a higher proton number. That means they have more electrons, because in a neutral element, the amount of electrons and protons are the same. So since this is a neutral element, it's not an ionic element, it's a neutral element, they have the same amount of outer shells. And because of this, the outer shells of the elements will be further away from the attractive force of the nucleus, and shells electrons more easily. And if you still haven't remembered, metals tend to give away their electrons, while non-metals tend to collect electrons. So that is why, as you go down a metallic properties of an element, as you go down a group, the metallic properties of an element increases. Now we are moving on to electronic configuration. We can obtain electronic configuration of an element from its proton number. From this, we will be able to deduce the proton number and the group number of the element. The electronic configuration of the elements in the periodic table is shown in this table. Now, in this table, we have elements of period 2. Period 2 is the horizontal. And here we have lithium, which is a metal, beryllium is a metal, boron is a non-metal, carbon, nitrogen, oxygen. So all these are non-metals, while these two are metals. Now, if each have their own specific group, and you have the electronic configuration. Now, here it says the proton number is 3. That means it has 3 electrons. Remember, when we say proton number, it just doesn't mean the proton, it means proton and electron, because as far as the atom is neutral, the amount of electrons and protons should be the same. So if we say in a neutral atom, or if neutral elements in a periodic table, and the proton number is 3, that means it also has 3 electrons in the atom. Now, since this lithium has a proton number of 3, the electrons will be 3. Now, here is the nucleus, which here in the center contains the neutron. The nucleus, which contains both the neutrons, and the protons. Then in the outer shell, it contains the electrons that travel around the shell. So here are the electronic configurations of period 3. Here's period 3. Have you noticed in period 3 they have a higher amount of proton number compared to as period 2. That is because, remember, as we're going down the period, they tend to have a higher amount of proton numbers. So, how are elements in the same period similar in terms of their electronic configuration? We have to look at the table again. Look at the table again, and you will notice that group 1 elements, if you look at the table again, you'll notice that group 1 elements have one outer shell electrons, while group 2 elements have 2 outer shell electrons. Group 3 elements have 3 outer shell electrons. Group 4 has 4, Group 5 has 5, Group 6 has 6, 7 has 7, and 8 has 8. So each group determines the amount of shell electron that is in the outmost shell. So if that is the electronic configuration, the number of the outer shell's electron is the same number as the group number of the elements. And elements with the same outer electron shells have similar chemical properties. Even in the period 3, the same thing happens. Group 1 elements have 1 in the outermost shell, Group 2 has 2, Group 3 has 3, and so on and so forth. So this means that each element has the same amount of electrons in its atmosphere with the group, depending on their group. So if you say, oh, this is a group, how we can reprove that phosphorus is a group 5 element, we just have to count the amount of electrons in its outmost shell. Let's move on to group number and the charge of ion. How are the types of ions formed by elements related to the group number? So you could see that each an ion is a neutral element that have lost or gained electrons. So that means it could have lost or gained electrons. Now, since the early group 1, 2, and 3 are mainly metals, and remember, metals give away electrons, they don't take, they give. So since the metals give away electrons, they lose electrons. That means plus, the charge becomes plus. Plus is not because it gained an electron, it's because it actually lost an electron and the entire atom became positive. That is a topic we learned in our chapter 12 and 11. And if you want to learn more specific on this, I highly suggest you watch those videos first. Now, group 1 elements, group 1, group 2, and group 3 elements have similar charge, except that group 1, group 2, and group 2 and group 3 all give positive ions, but they all have different type of charge. They have 1, 2, and 3. Examples: sodium, potassium, magnesium, calcium, and aluminium. The elements in group 1, 2, and 3 are metals and tend to lose electrons to form positive ions. That is because metals give away electrons. The charge of the ion is to make the same as the group number of the element formula. Now, if we move on to group 4 and 5, elements tend to form covalent instead of ionic compounds. So instead of creating ionic compounds, ionic elements, and so on, it actually forms covalent compounds. The elements in group 4 and 5 share electrons to form covalent bonds. So remember, there's two different types of way of bonding. We have metallic bonding, ionic bonding, and covalent bonding. So elements in group 4 and in group 5 don't give or take electrons. They share the electrons to form covalent bonding, and they have a maximum oxidation number that is the same as the group number of the element. And if we move on to group 6 and 7, we have negative. So group 6, 7, groups the group 6 and 7 have negative and produce negative because the elements in group 6 and 7 tend to have non-metals, and non-metals gain electrons. They don't give, they gain. So they will have negative ionic elements. So this doesn't mean that it lost an electron. It gained 2 and the entire atom became negative. And the 2 is to indicate the amount of electrons that it lost or gained, and the signs just show whether it gained or lost electrons. So don't think, oh, it lost 2 electrons. No, it actually is because it gained 2 electrons and it became negative. Now, because they are non-metals, they gain electrons. They are non-metals and they tend to gain electrons to form negative ions. Now, finally, group 8. Group 8 are what we call noble gases. These elements do not form compounds or react whatsoever. They have a stable electronic configurations and they do not form compounds. That means they are quite unreactive. Now that we've understand the trends in the electronic in the group number and the charge of ion, now we're going to learn about the trends in group. Mendeleev, a Russian chemist, created the first periodic table in 1869. He arranged the elements with similar properties into the same columns in the table. He predicted existence and properties of new elements based on the trends in the properties of the elements in the group. And he knew that Mendeleev was able to predict the properties of new elements based on trends in the properties of the elements in the group. That is how he knew. So the increase in atomic size and metallic properties as it goes down and as it goes up, increase in electronegativity, the tendency to attract electrons, and ionization energy. Energy needed to be extracted. Energy needed to extract an electron from an atom. So now we're going to on to section 13.3, group 1 elements. Here we're going to be learning about the group 1 element. So what is so special about the group 1 element? Well, in this section you will find out. We're going to learn about them and describe the alkali metals that are relatively soft metals and the general trends down in group 1. So let's move on to, this picture is blurred, okay. Group 1 elements. The elements in group 1 of the periodic table are called alkali metals. Alkali metals have similar properties since they belong to the same group. Now, what are the main properties of alkali metals? Now, this is something you have to note down and memorize for your IGCSE exams as they might come out. The physical property, there are two types of properties: physical properties and chemical properties. Now, the physical properties of alkali metals are that 1. Alkali metals are soft. Very surprising, but turns out that actually group 1 metals are actually very soft and can be cut easily with a knife. they have low melting points and boiling points. So alkaline metals have low melting points. That means you can easily melt them with low temperatures. Not so low though. Temperatures like 50 degrees Celsius or 70 degrees or 100 degrees Celsius is enough to melt a group 1 is enough to melt a group 1 metal or an alkaline metal. They also have low density, e.g. lithium, sodium, potassium, all float on water. Yes, this is because of the low density. Because of that, they float on water, and when freshly cut, alkaline metals show a shiny and silvery surface. The shiny surface becomes dull very quickly. That means when you freshly cut it, the metal becomes really shiny, but as not long, it turns really dull and dried, I guess. So here are all the alkaline metals. Here are the group 1 elements. The vertical group 1 metals. We have lithium, sodium, potassium, rubium, calcium, and thorium. So going down the group, the melting point of the metal alkali decreases and the density of the metal genetically increases. As you move on here, that how the physical properties change as you go down the group. As you go down the group, the melting point of alkali metals decrease. That means this this metal this metal has the lowest melting point, while lithium has the highest melting point. Now, because of that, the melting point of alkali metals decrease, and the density of the alkali metals generally increase. So lithium, sodium, and potassium are the only metals that can float in water, while the rest have enough density to cause them to sink in the water. Now, how can we use the periodic table to predict the properties of alkaline metals? So here are alkaline metals. As you could see, lithium has the highest melting point with a melting point of 180 degrees Celsius, while the density per gram centimeter cube is 0.53. This is a very low density and a very okay melting point. But as we go down the group 1, as you can see, rubidium has a melting point of 39 degrees Celsius, which is way much less than the lithium melting point, but it has a much higher density, literally double the density of more than double the density of lithium. Now, alkali metals decrease down the melting point of alkalis decrease down the group. Hence, the expected melting point of calcium, the element below rubidium, is to be below 39 degrees Celsius. In fact, it is 29 degrees Celsius. And because of this trend, we can the melting points predict the melting points of the metals after rubidium. Since calcium is right below rubidium, it should have a lower melting point than rubidium and a higher density than rubidium. And this is how Malandiv was able to predict some of the elements in the periodic table. Now here are the chemical properties of alkaline metals. Alkaline metals are highly reactive metals. Remember, we just talked about the physical properties. Now we have the chemical properties. Now the chemical properties of alkali is they're really highly reactive metals. They are stored in oil to prevent them from reacting with air and water. Do all alkaline metals have the same reactivity? In order of reactivity, lithium is lesser than sodium, and sodium is lesser than potassium. So that means potassium has the highest reactivity than sodium or lithium. And if you haven't noticed, it's decreasing down the group. So meaning that as you go down the group, the reactivity increases. Hence, the reactivity increases as you go down the group because it's easier to lose the outer shell electrons from the bigger atoms. Now, alkali metals react with cold water to form alkali and hydrogen. Example, lithium quickly reacts with water as to form lithium hydroxide and hydrogen. Oh, sorry, excuse me, I lost. It quickly reacts to form. Okay, so it quickly reacts to form hydrogen, lithium hydroxide and hydrogen. Sodium reacts violently. Sodium darts around the water's surface and reaction may be explosive. So sodium plus water gives sodium hydroxide and hydrogen. Now potassium reacts very violently and reaction is explosive. That means there will be spark and can even cause a fire. As you can see, the reactivity series, lithium is the lithium being the lowest has the lowest reactivity compared to the others in the reactivity series, with this having the highest reactivity in the group 1 metals. So now let's move on to 2. Alkali metals are powerful reducing agents. Reducing agents are agents that reduce themselves to get another element in a reaction oxidized. So here we have alkali metals form ions charged by losing one in its outer shell. Sorry, excuse me. Alkali metals are powerful reducing agents. That means they reduce the substance that reduce other substances to oxidize itself. Sorry, I got it wrong. It doesn't reduce itself. It reduces other substances to oxidize itself. That is a reducing agent. We learned about that in our chapter 11, which you could watch in our channel. All alkali metals form ions with a charge of +1 by losing one electron to form from the outer shell. Example, lithium loses an electron to become a positive ion and has an extra electron. Their reducing power increases down the group. That means as you go down the group of the group 1 element, you will get a higher reducing power. 3. Alkali metals form ionic compounds. The compounds have a similar chemical formula and are soluble in water. Soluble in water means that they can dissolve in water and they have similar chemical formula. That means they can form ions. Why? Because most of the all the group 1 elements are metals. Most of them anyway. Now we're going to section 13.4, group 7 elements. Group 7 elements. This is group 7 elements. Here we're going to describe group 7 elements as halogens, as diatomic nonmetals, and describe the turns down in group 7. So, in the group 7 elements of the periodic table are called halogens. The group 7 elements of the periodic table are called halogens. The elements in the group are fluorine, chlorine, bromine, iodine, and acetylene, as you can see, and they are the final group before arriving at noble gases. Now, what are the physical and chemical properties of halogens? Halogens are nonmetals that exist as a diatomic covalent molecules. That means you write them with a 2 right next to their element symbol. They have low melting and boiling points and they are colored. They give a summary. Now we have, you can see, chlorine and bromine and iodine. Iodine is solid while bromine and chlorine is gas. The melting and boiling points intensity of the halos increases down the group. That means as you go down the group it decreases. That means fluorine has the lowest melting and boiling point, while acetylene has the highest melting and boiling point. So it increases as it goes down the group. Now, as you go down the group, the melting and boiling point increase and the density increases. The colors become darker as the color intensifies and looks more saturated in color. As you can see, chlorine is a pale yellow green yellow green gas, while bromine is a red brown. Notice how bromine seems to have more color than chlorine, and iodine is a solid, it's not even a gas, and it has a gray black solid. So how can we use periodic table to predict the properties of halogens? Since the boiling point of halogens increase on the group we should expect the halogen above chlorine is to have a boiling point lower than negative 34 degrees Celsius. Chlorine is a gas that boils at negative 108 degrees Celsius, while similarly we should expect that the halogen below iodine to have a boiling point greater than 184 degrees Celsius. Acetylene is a solid that boils at 337 degrees Celsius. So that means as you go down the boiling we can predict it, because as you go down the boiling and melting point increases, so we can predict what we can predict what is coming, what is next at the element, what's next in the group. Let me just put this here. So now let's move on to the chemical properties of halogens. Now, halogens are reactive nonmetals. Each halogen has 7 outer shell electrons. This is because they're in group 7. Only one more electron is needed to achieve the stable electronic configuration of a noble gas. Because you're wondering, why do elements try so hard to get a full outer shell electron? They do this because they want to have a configuration of a noble gas. Noble gases have full outer electrons. That means they are fully reacted. And they can react because they don't need to give or gain any electrons. Now halogens, since they have 7, the max outer shell of an electron is 8. You need 8 to have a complete full electron shell. Now halogens, they have 7, so all they need is just 1 more. So obviously, unlike the group 1 elements, they aren't just going to give away, they're going to take, because they just need 1 last electron to get the configuration of a noble gas. So what is the order of reactive halogens? The reactivity of halogens decreases down the group. This is because the size of the atom increases down the group. This makes it more difficult for the nucleus to attract 1 more electron. So since it's taking an electron and not giving an electron, if the reactivity of the element in group 7 decreases as you go down the group. So now let's move on to some chemical properties. Halogens undergo displacement reaction. A displacement reaction is a reaction in which one element takes the place of another element in a compound. A more reactive halogen will displace a less reactive halogen from its halide solution. In this reaction, we have chlorine and sodium bromide. Chlorine is a light yellow gas, while sodium bromide is a colorless aqueous liquid. No, but in this reaction, chlorine is aqueous too. So in this case, chlorine is going to replace bromine to form sodium chloride, and bromine is going to take chlorine's space to form just itself. It's going to leave. So chlorine took bromide's space. Why? Because chlorine is more reactive than bromine, so it took the place of bromine. chlorine was like, hey, I'm more reactive than you, so give me your spot. And it gave bromide did give it a spot, leaving it to be on its own. Bit harsh, don't you think? Now we have a table of the displacement reaction of some halogens with potassium halide. Now chlorine displaces bromate from a bromide solution, and chlorine will also displace iodine from an iodide from an iodine solution. The displacement reaction of some halogens are summarized in the table. A less reactive halogen can displace a more reactive halogen to form a halide. Now let's move on to the next part where they explain two. Halogens are more powerful oxidizing substance. That means a substance that oxidizes other substance while reducing itself. Now, during a chemical reaction, atoms of a halogen readily gain electrons to form halides, ions with a charge of -1. The displacement reactions between halogens and other halide ions can also be classified as redox reactions. Redox reactions are reactions that have both the oxidation and reduction happening in the same reaction. Now, redox, consider the displacement reaction between chlorine and potassium bromide. The overall ionic equation is this. Chlorine here acts as the oxidizing agent, while bromide ion acts as the reducing agent, and while fluorine is the strongest oxidizing agent. The oxidizing power of these halogens decreases down the group. Now we move on to the next section, which is 13.5 transition elements. I told you, remember when I showed you the periodic table with some of those metals having no group whatsoever. Now we will learn about them in this section, the transition elements, and what are they really. So some elements found between group 2 and group 3 are known as transition elements. Transition elements are also called transition metals because all of the transition elements are, well, metals. So now we're going to learn about the properties of transition metals. Transition metals have high melting points and high density. Notice that the melting point and density of the transition metals are higher than those in group 1 and group 2. This is true. They have high melting and boiling point. These are chromium, manganese. They all have elements with different melting points. Now if you notice, group 1 and group 2 have quite low melting points compared to the transition metals, who have up to 1K plus when it comes to melting and boiling points. And the density is also way much higher than those of group 1 and group 2 metals. So let's go to the next point, which is transition metals can form colored compounds. Transition elements can form colored compounds. One of the most significant features of transition metals is that they usually form colored compounds. The colors of the compounds of a transition metal are different at different oxidation numbers. The table given shows the color oxidation numbers of some transition compounds. As you can see, some of these transition form color compounds when they react. The colors of the compounds of the transition metal are different at each different oxidation number. So here we have chromium 3 chloride, so iron 2 sulfate, manganese 4 oxide, and copper oxide. Now you see that they form a colored compound. When they react to form a compound, it tends to be colored: green, pale green, black, red, orange, yellow, purple, or even black. So now let's move on to 3. Transition metals and the compounds are good catalysts. Well, a catalyst is a substance that speeds up a reaction without getting unaffected by the reaction. That means that they don't get reacted or used up when reacting, and they speed up the reaction. They Our at transition metals at their compounds are important catalysts and for many reactions, both in the laboratory industry, such as iron, which is needed for act as a catalyst in the Haber process, and nickel, who act as a catalyst for the manufacture of margarine from vegetable oil. See chapter 10 and chapter 17. We haven't arrived on chapter 17 yet, but we have done chapter 10 and made a video about it, so you can watch if you don't think you've made a good understanding on that chapter. Now, excuse me. Now, transition metals act as good catalysts as they speed up the reaction by lowering the activation energy. And the final one is transition metals have variable oxidation numbers. Unlike metals in group 1 and group 2, transition metals form iron with variable oxidation numbers because they form variable oxidation numbers. We find that metals in group 1 and group 2 form one type of positive ion only. For example, group 1 metals form ions with oxidation number of +1, while group 2 forms oxidation number of +2. Group 3 forms oxidation number of group 3. But however, for transition metals, there is no specific number. It can vary sometimes. Unlike the metals in group 1 and group 2, transition metals form ions with different oxidation numbers, and the table shows the variable oxidation numbers of some transition elements in their compounds. So now we move on to the last section of this chapter, which is 13.6. Here we talk about noble gases. Here we're going to learn about what a noble gas is and how is their properties of noble gases. Now, noble gas, the elementary group 8 are called noble gases or inert gases. Why? Because all of them are gases to start with, and two, they are unreactive. Why? Because they have a full outer shell. That means they do not have to react to get a full outer shell. They don't need to lose or gain electrons. This means they do not form ions, they do not form oxidation, they do not have oxidation numbers, they don't act as catalysts, and they are pretty much very unreactive. So now we have the elements in the group are helium, neon, argon, krypton, xenon, and radon. The properties of normal gases. Normal gases are monatomic, and they are also colorless gases at room temperature. They have low melting and boiling point, and are also insoluble in water. That means they can't react with water. They have low melting and boiling point, and they are unreactive. So how come noble gases are reactive? Well, they have a full electronic configuration that makes the noble gases unreactive. They do not lose, gain, or share electrons, and hence they are rarely react to form compounds. As noble gases are unreactive, they are often used to provide an inert atmosphere. Argon is used to fill tungsten bulbs. It provides an inert, unreactive atmosphere that prevents oxidation of the filaments. As you can see in this cartoon image, you have fluorine taking an electron and neon not taking an electron. Why? Because it already has the enough electrons needed, but fluorine doesn't have so and is looking to gain one more electron. Now we have arrived at the end of chapter 13. Here is the final section mind map, where you show the periodic table, the groups which are vertical columns, and the periods which are horizontal columns. Then we have the metals and non-metals, like transition metals and group and alkali metals. Then we have halogens and normal gases. So this is the end of our chapter 13 video. Thank you so much for watching. If you think you've understand, why don't you hit that like button and subscribe to our videos so you could learn more. And we'll see you all in the next chapter. And if you have any questions or something you don't understand, you can always rewatch the video or watch our previous videos. We have made videos on both chapter 10, 11, and 12, so you could understand fully on each chapter. So thank you all so much for watching, and I'll see you all in the next time. Goodbye.